Hello everyone. So we will have one small section that sort of recapitulates how we used mathematical modeling techniques to understand population growth. So the goal of there will be some small elements of new learning, we will have new concepts, but broadly follows the previous set of lectures starting from single species, discrete generation population models all the way to two species competition models. A bit of recap just so that students find using mathematical thinking and sort of get used to thinking in a mathematical way. Okay. So we started off with learning exponential or geometric growth in populations, right. So the basic idea was really simple. The population at a next generation was basically lambda times the population at the previous generation. So what was this lambda? This lambda contained the following terms: 1 which represented the current population, and a term b that captured the number of offspring that were born to each individual, minus d that captured the probability of death of an individual in this one discrete unit time. And as I mentioned, the discrete unit time biologically could be thought of as one generation, right. And we also write this as Rd. So lambda is sometimes called finite rate of increase, I prefer the term growth factor. I call this factor because this really is the factor by which the generation k becomes generation k plus 1, right. Okay. And Rd is basically the geometric growth rate. In some sense a measure of fitness per generation, right. It is the growth rate in the unit of generations, right. And with this simple model we studied a number of simple implications, and the implications were the first and foremost were, okay, when lambda was greater than 1 we had an exponential or geometric growth of populations. Okay, on the other hand, if lambda was less than 1, there was basically a geometric or an exponential decline. So we use the word geometric instead of exponential for discrete time systems, but I sometimes use them interchangeably because mathematically they are sort of have this exponential growth, right. Okay. And we also talked about doubling time. How much time does it take for how much time does it take for population to double for a given value of lambda, right. So it was given by this simple formula: tau is log 2 by log lambda. Larger the value of lambda, smaller the doubling time. So faster the given population reaches its twice the capacity. And a crucial point to this discrete time geometric population model was that a crucial assumption behind that was that there were unlimited resources. Okay. The moment this assumption is not right, the populations will not obey this equation, and therefore the outcome that the population is increasing exponentially will not be true anymore, right. Okay. And so therefore that gave us to the general concept of density dependence. So before we think of density dependence, it is useful to sort of move to continuous time and represent dn by dt represents the rate of change of populations using the notations of calculus. So dn by dt represents the rate of change of population size, right, and whereas 1 over n dn by dt captures the per capita rate of population size, okay, or simply dn by dt is the growth rate, whereas 1 over n dn by dt would be per capita growth rate, okay. And if we plot on the y axis the per capita growth rate, and if this is a constant, this would be called density independent population growth. And that is precisely what also leads to exponential population growth if this constant is positive. On the other hand, if the density dependence is present, in other words this per capita growth rate is a declining function of the population size, okay, then we say the population has density dependence, and in the specific form that I have written, the value of population size at which the per capita growth rate becomes 0 is basically the carrying capacity. This leads us to the logistic population model. Now of course what we now have is an ordinary differential equation. Ordinary differential equation sometimes can be incredibly hard to solve, okay. So therefore we use this trick or a method called the graphical analysis, okay. Or a geometric way of analyzing the system. This geometric way of analyzing the system involved two things. The first thing is identify what are called equilibrium, and then identify the stability of this equilibrium. So what is geometric about this? The basic idea is that we plot the right hand side functional form of this population dynamical model. So basically on the y axis we write dn by dt, on the x axis we have population size n, and we then plot how does this graph look like. For the logistic model, this graph looks like this, where this is 0. So the growth rate is 0 when the population size is 0, okay. On the other hand, growth rate is also 0 when the population size is k. Okay. Now, equilibrium are basically those population sizes at which the growth rate is 0. Okay. So, equilibrium are defined by this, the growth rate is equal to 0, and clearly population size equal to 0, when there is no individual, there is nothing to grow, right. So, growth rate is 0, and when this population has reached carrying capacity, again it is at an equilibrium. Okay. So, that defines the equilibrium. Now, what is the stability then? The stability is the notion that if we make perturbations from the equilibrium, what happens to the system? If the perturbation decays, we call that a stable equilibrium. If the perturbation increases in size, we call that unstable equilibrium, right. So, now let us see what happens if we apply this principle. If I make a small perturbation away from the equilibrium here, so this is shown by this green dot, the growth rate at this point of population size is positive. So, therefore, the population will increase further and lead to a larger population, and again at this point the population size is large and the growth rate is larger, therefore, the population will increase further, and as you can see in this entire window between 0 and k, the population curve, the blue line is a positive growth rate. That means the population will keep on increasing wherever you start between 0 and k. On the other hand, if I were to start population for values greater than k, meaning above the carrying capacity, the blue line is now below the 0 values and it is negative, therefore, the population will decline. So, what this is called a flow diagram, right, and what we learn from this flow diagram immediately is that 0 is an unstable equilibrium, which I am denoting by red circle here, whereas carrying capacity is a stable equilibrium, which I am denoting by a solid green dot. Okay. So, this becomes an unstable equilibrium and this would be stable equilibrium. Now, to sort of conclude how the population changes with time and how does it depend on the initial population size that you may have, I did not have to solve the differential equation completely. I just had to plot a graph, and from the graph I had to check the various signs. Is the growth rate positive or there is a growth rate negative? If the growth rate is positive, population will increase. If the growth rate is negative, the population will reduce. So, I had to use only graphing skills as well as identifying the signs and interpreting what a positive growth rate means. So, this is called the graphical or geometric analysis that does not require us to explicitly solve differential equations, and therefore, this method is really powerful. And having learned this, let me now introduce a concept which I have not done so far, which is that of Allee effect, which I am sure ecologists who have studied would be familiar with. So, Allee effect is a scenario when low population sizes are not viable. So, this happens for example due to difficulty in finding mates when the densities are really small. This happens in socially living organisms. If the numbers are too small, the group sizes might be really small, or the chances of finding a group might be really small, therefore, the mortality rates might be high, the mating rates might be low. Put together the populations become unviable. Okay. So, to represent this, we can again plot the per capita growth rate. To sort of contrast Allee effect with that of the previous logistic model, let me first plot the logistic model, which looks like this, okay, where the per capita growth rate starts with a large value because low population size means low intra-specific competition, and as the population size increases the competition increases, therefore this per capita growth rate is reducing. However, if you now include the Allee effects, what happens is that for low population sizes the per capita growth rate is actually negative, because populations are not even viable. Only when the population exceeds a certain size, let us call this NC, then only the populations become viable, and then eventually again at carrying capacity they follow the same trajectory as the logistic model beyond certain population size. But the key part here is this, where the population growth rate is actually negative up to NC, and the population growth rate is positive only beyond NC, and in fact up to this point where the two lines are intersecting, the growth rate is actually increasing with population size, meaning the larger populations are beneficial to individuals. But eventually the resource limitation kicks in, and therefore the large population size behavior is similar to the logistic model. Okay. So now what happens, what do you think will happen in this case? To understand this again, of course we can write down differential equations and solve them, and that might be actually unnecessary if we were to think of what would be the population growth rate as a function of n, right. So if you now plot the population growth rate for this, let me mark the points NC and let me mark the point K. Remember that basically I have to take the blue curve here and multiply it with r times n, where r is the intrinsic growth rate and n is the population size. Okay. With some if you go back to the math refresher and practice your graphing skills, you should be able to do this. One thing to note is that if the per capita growth rate is 0, population growth rate will also be 0, right. So therefore this curve has to again intersect 0 at both NC and K, and what we will find is that this will be the shape of the growth curve now. This is in contrast to the logistic population model, which had basically a quadratic shape. Okay. Now let us identify which are all the equilibrium. Equilibrium are all the points where the population size is 0, that would be this 0, population size 0, population size NC and population size K. Now again look at what is the growth rate of the population for various population sizes. Okay. Now let us look at this window between NC and K. In this window between NC and K, the population growth rate is always positive, therefore anywhere I start in this window the population will increase. Again, as like the logistic model, if I go beyond population carrying capacity, the growth rate will be negative, therefore the population will reduce in size. And interestingly, between 0 and NC, okay, the growth rate is negative. Therefore, if I start the population in this window between 0 and NC, population will actually decrease in size and will reach 0. So therefore, this intermediate point is now the unstable point, whereas both the 0 equilibrium and the carrying capacity equilibrium, they are stable. So therefore, in Allee effect, population size 0, which is basically extinction, is stable. In addition, carrying capacity is also a stable equilibrium, and to make the populations viable, the initial population, the initial value of the population must be greater than NC. Only if the initial population is in this window, the population size will increase. Okay. And this is a really useful and powerful technique to arrive at how populations change with time without actually solving differential equations. Okay. And having learnt about how populations change, because of intraspecific competition as well as other factors such as mating and social behavior. We can think of now two species systems. There are many two species systems, right, and the one that we studied was that of competition. However, there are many ecological interactions such as mutualism. Then we can have interactions which are predator prey, and then we have host parasite interactions. To study any of these type of, and there are of course many more, to study any of these type of interactions, we now need to write down equations of the form how does species 1 change with time and how do species 2 change with time, what is the growth rate for species 1 and what is the growth rate for species 2. Of course, we learnt how to write these equations only in the context of interspecific competition, right, in addition to intraspecific competition, right. So, now but the general formalism of these differential equations can be used to describe many of the other systems as well, and in those cases we can replace the specific forms with a more general form such as this. The growth rate of species 1 depends on both the number of species 1 and number of species 2 individuals, and the growth rate of species 2 depends on number of species 1 and number of species 2 individuals. And then now we have what are called coupled differential equations, and again we do not have to mathematically solve this. We can look at the structure of equilibrium, we can do the kind of analysis that we did for competitions, right, such as if I start with only one species, can the other species, if the other species is now introduced, what do we expect, and vice versa, and we can repeat those types of analysis, but with additional mathematical skills one can actually analyze these dynamics much more completely. It turns out that we now have not only stable equilibrium and unstable equilibrium, we can also obtain cyclical populations when we have two species, okay. And in fact that is precisely what happens when we have a predator and prey, and the analysis of that is something I am not going to cover here because that requires a few additional mathematical skills, and I would encourage you to look at the reference by Allee, A Primer of Ecology. Which covers some of these additional models. With that note, I will sort of stop the refresher of what we have learnt across the population modeling exercises. In the future classes we will learn about metapopulations, how space influences the dynamics of populations, and including various case studies, okay. Thank you very much, and we will be in touch over the live sessions.